Do you all see the screen? Everyone, do you all see the screen? Give me a second. Yeah. Just drop a chat again. I'm not able to see the chat. One second. Okay. Okay, just give me a second. Yeah, I think this should do. Yes. Yeah. You can see the window, right? Okay. All right. So talking about this unit, right? So firstly, I hope you all know what discrete mathematics is meant for. So talks about the discrete subjects. Okay, these are all discrete concepts in mathematics that are together studied under discrete mathematics, something that is not very continuous. Okay, so you must have learned many concepts here. Okay, I think Anand have covered something like Pigeon hole principle. Okay, I think Fazil have covered math relation as well. All right. So now we are stepping onto another domain called recurrence relations. Okay, recurrence relations is very important. You'll be learning that. I think you have it in your data structures course as well, and you will be learning that in your design analysis and algorithms course, DAA. It is very important. So I want you to pay attention to this very carefully. Okay. So we are starting with the understanding of recurrence relation. Then what do you mean by solving a recurrence relation? And then we'll quickly go to the methods of solving recurrence relations, few practice examples for them, and we'll close for the class for this unit. Yeah. Is this clear? Yes. Great. So moving forward with this, recurrence relation. So what does the name suggest you? So you must learn to recursion, right? What is recursion? Something that calls itself, right? A function that calls itself is under recursion. That's what you call it. What do you mean by recurrence relation? Kind of relation. It's a kind of some kind of equation or something, right? So the in that equation, what do you have? You have a variable or a function that is dependent on itself. Okay, itself. By itself, I mean to say, let's say we have a function that is called t of n. Okay, t of n is dependent on t of n itself, meaning it could be n minus 1 or n minus 2 or n minus 3, but it is still dependent on the function called t, where just the input is changing from n to n minus 1. Right? It could also be n plus 1 also. Okay. So generally the equations that you are going to see are going to be in this form. T of n is equal to T of n minus 1 plus T of n minus 2 or something like that. Meaning some n in terms of n minus 1 n minus 2 or something like that you have. Right. Why not? You can also have it in terms of this. N plus 2 is equal to n plus 1 plus T of n. Do you think that both the equations are same? Solving this equation is equal to solving this equation? Because end of the, you can just substitute n plus 2 is equal to T. That'll do the job for you. T of t is equal to t of, I mean, not this t, so small t. Don't get confused. T of t is equal to t of t minus 1 plus t of t minus 2. Okay. So just making that point here, we'll quickly move forward to understanding recurrence relation. What do you mean by a sequence? A sequence is a set of numbers that follow some pattern. Correct? Anything, any pattern. So a general sequence is represented in the form of explicit form. Okay. So explicit form is simpler. It is just expressed in terms of the number I'm speaking for, meaning let's say I have a sequence like 1, 3, 5, 7, 9. What is this? This is odd number sequence. I can represent a general term in that in terms of what? In terms of 2n minus 1, right? 2n minus 1 with a condition on n that is greater than or equal to 1, because then if n is equal to 1, then n will become minus 1, and I don't want that in my sequence. So what I'll do? I'll put n is greater than or equal to 1. This is also called as initial condition. Initial condition. Okay. So moving forward, an is equal to 2n minus 1 is a simple explicit form, meaning the function is dependent directly on the value of n, right? But many a times you will not have such things. Many a times you will have an dependent on an minus 1, an minus 1 dependent on an minus 2, and all that, right? You don't want that. You want the function to be dependent on just n, just n. So in that case, what you will do? You will solve such equation. You will solve such an equation. So solving recurrence equation or recurrence solution is nothing but putting the recurrence relation to the form of explicit form. The explicit is just the English meaning, right? Same explanation. It is directly dependent on the value of n or whatever, right? Great. So is this clear? Can we move forward? Is this clear? Yes. Okay, great. Now, these are just few examples for you to understand recurrence relations before going into it. I didn't see that in your notes, but I just want to cover this, right? What is the recurrence relation for n factorial? We very well know this. N factorial is what? Let's say an is equal to n factorial. We very well know that n factorial is n into n minus 1 factorial. So in that case, we can say an is equal to n into an minus 1, right? N into an minus 1, right? Where n is greater than or equal to 1 because we have not defined anything for. If you put n is equal to 0, we have not defined anything for a minus 1. That does not make sense. So if n is equal to 1, a not even is defined. A 0 factorial, right? So that is there. Moving forward. Similarly, Fibonacci an is equal to an minus 1 plus an minus 2, where n is greater than 2. Because we have defined it only for a starting from a1. So this has to become 1, right? An minus 2. So for that reason, at least n should be greater than 2. Again, should it be the way it is defined? No. Okay. It is fully up to the comfort of the person who's deducing this recurrence relation. Whoever is writing this recurrence relation can modify it in such a way which terms should come and which terms should not. And in the same way, whenever you're given a sequence and you want to find this general term of that sequence, what you should do, you will try something like this, right? You will get an answer, but you might have a doubt. What could be the initial condition? You will just plug it in. Just plug the value and check it. When you plug the value and check it, you will automatically get, okay, these are the terms which are getting generated. This term are generated. So I have to include that in my initial condition. As simple as that. Okay. Moving forward. Yeah. Can someone please confirm if you have this solving recurrence relation, making an explicit form to recurrence relation? Do you have that? Your syllabus? I think you should have the other way around. You must have that. But do you have explicit to recurrence? Just tell me quickly. No one is certain. Okay. No one is certain. Okay. Do you want me to teach it? Okay, I'll give you a glimpse of it. Let me know if you don't understand this. Okay. But I don't think I have seen it in the notes. So Sn is described based on n. N is the variable, explicit form variable, right? So Sn has given us a into 3 power n plus b into minus 4 power n for n greater or equal to 0. Fine. Now you have to represent Sn in terms of Sn minus 1 or Sn minus 2. That is the key idea here. So what you will do is very simple. Take Sn minus 1. So substitute n instead n minus 1 instead of n. In all the places, substitute n minus 1 instead of n. So you will get a into 3 power n minus 1 plus b into minus 4 power n minus 1. Now you will try to write this guy in terms of that guy. You will try to write Sn is equal to a 3 power n plus b minus 4 power n. Just make this equation look like that equation. How will you do that? Very simple. You have to first find what? You have to first make it 3 power n. This was 3 power n minus 1. So what they've done, they've taken the 3 outside. Similarly, minus 4 power n minus 1, they'll take the minus 4 outside. This is just minus 4. Okay. And then you got a term for Sn minus 1. Just cancel out the common variables. Just adding equations, subtracting equations will get you an equation in terms of Sn and Sn minus 1. They've just done that. And after that, you will get this kind of equation where Sn and Sn minus 1 are related together after cancelling and all that. Okay. Now you will make n in terms of n minus 2 again. You got n minus 1, but you still have variable b and all that. You don't want that, right? I don't want such things. So what I'll do n in terms of n minus 2. right? So now I substitute that. So what happens in that case? Just give me a second. It gets loaded. Okay, yeah. In this case, n in terms of n minus 1 would do. Why? Because, I mean, n minus 2 also works. It does not say it's wrong. Okay. But you want Sn in terms of Sn minus 1 and minus 2. If you substitute as n minus 2, it becomes Sn minus 3. Right? So just n minus 1. Again, that will give you n minus 2 law relation without any constant. You just cancel out the initial equation and this equation. You get something in terms of Sn minus 1 and Sn minus 2. See the beautiful equation. What equation you had previously and the equation which you have now, right? So this is a recurrence relation. Just to, okay, if you have that, you can always go through this. Fine. You have this in my notes. I share the notes at the end of the class. Okay. Yeah. Moving forward with the first concept of recurrence equation solving. Firstly, let set A and B a sequence of real numbers. 1 second, guys. He's testing my patience. Please give me a second. Yes. Let the set an be a sequence of real numbers, with an being the nth term. A recurrence relation of the sequence is an equation that expresses an in terms of one or more of its earlier terms. An expresses in terms of an minus 1 and minus 2 and so on. It is also called a difference equation. And the general form of the recurrence equation is this. Just note this down, the general form. C naught an plus C1 an n minus 1 plus C2 an minus 2 plus still Ck n minus k, that is equal to f of n. Please note this down. We'll be using this in further concepts. Okay. So what happens? Yeah. Sorry, guys. Am I audible? Am I audible? Just give me a second. Give me a second. Yeah, just confirm if I'm audible now. Yes. Okay. Okay. Yeah. I think the recording is still on. No worries. Yes. Okay. Screen is also visible, right? Not getting notification base. 1 sec. Okay. 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 It's fine. We'll quickly complete it then. No worries. So this is a general form of the recurrence relation. Yeah. So what you are going to do here is you have to find a mechanism for solving this equation in such a way that it is not dependent on itself. Correct. So what you'll do is, let's say there are different forms of solving equations. Okay. There could be the different kind of things. In this case, the general form, all the coefficients could be constant. All the coefficients could be in terms of n also. Okay. The right hand side could be either zero or non-zero. Right. And you could have different degrees of this equation. In that mechanism, you solve it differently. Okay. So considering all these factors, we are understanding how to solve this appropriately using such a method. Okay. So now in the first method, which we are going to see, we will be only having, were you taught iteration method or substitution method, something like that? Iteration, substitution. Okay. No one is certain. Okay. All right. Okay, so what happens here is, here, if all the constants C naught to Ck are constants, then you call them linear recurrence relation, right? Most of everything we have is linear. We won't have any constant in terms of n. That C thing in terms of n. We won't have that things. Okay. If the right hand side is zero, you call it homogeneous, else you make it non-homogeneous. Next, the order of the recurrence relation is very important. We'll be using that in characteristic root as well. It's very simple. It's just the this guy an, right? The postscript you have minus the extremmost guy n minus k, right? N till n minus k you're extending, right? So the degree is going to be, the order is going to be k. Okay, so it's going to be uh, for this equation Sn minus 5 Sn minus 1 is equal to 1. The order is simply n minus 1. That is going to be simply 1, first order recurrence relation and all that simple. So we are first going to see a simple method called iteration. I'm not sure if you have it. I'll just quickly cover it up. Then we'll go to characteristic root, generate a function, close to the class. Iteration method is simple. You just have to substitute on the same guy again and again. Substitute on the same guy again and again. Okay. You'll be learning that in our DAA course as well. So an is equal to an minus 1 plus n minus 1, where n is greater than or equal to 2 and a1 is equal to 2. Understand this. This a1 is equal to 0 guy might seem like a very, very poor guy. No one is minding him. But this guy is very important for solving a recurrence relation. If you don't have this guy in recurrence relation, no, you cannot solve the recurrence relation. That is the truth. You cannot solve the recurrence relation. Okay. So just mind that you are paying some good respect to this guy. Yeah. Next. What happens here? An is calling an minus 1 and he's adding n minus 1. Okay. So what happens then? What will be an minus 1? So substitute n minus 1 in terms of n. So an minus 1 would be an minus 2 plus n minus 2. Then what would be an minus 2? An minus 2 would be an minus 3 plus n minus 3. Right? Wow, so nice. So let's try to substitute this guy there. Right? An minus 2 substitute there. It will give you what? An minus 3 plus n minus 3 plus n minus 2. Agreed? So an minus 3 plus n minus 3 plus n minus 2. Then let's substitute a n minus 1 there. So what will be that? It will be a n is equal to a n minus 1, sorry, a n minus 3. You are substituting in terms of a n minus 1. So a n minus 3 plus n minus 3 plus n minus 2, and already n minus 1 is there, right? So you clearly see the sequence, right? So we can extend this to up to many, many terms. So a n can be reduced to many terms. So a n minus k in general, let's say. It will stop at k, let's say. So a n minus k. So it will be what? N minus k, n minus k minus 1, n minus k minus 2, and it keep extending until n minus 3, n minus 2, and n minus 1. Getting this? Getting this? So what happens in this case actually? So it has to stop at a point, but where will it stop? We very well know where it stops. What is that? Initial condition. Just go through that. So initial condition is a1 is equal to 0. So it has to stop at a1 at least. A1 at least, right? So if it is a1, right? If it is a1, the next term would be what? 1. Because if it was a n minus 3, it was n minus 3. A1, it was 1. It should be 1. Then if this is 1, this has to be what? 2. Because n minus 3, n minus 2. So 1, 2, 3 till what? Till n minus 3, n minus 2, n minus 1. That's it. Okay. And we were clearly given that n minus 1, a1 was 0. So this will become 0. So this is just sum of n minus 1 terms. Sum of n minus 1 terms, I hope you all know it. It is n into n minus 1 by 2. Okay. So yeah. So that is it about iteration method. Just a quick glimpse. Let me know if you don't understand anything. Yeah, after the end of the session. Next, moving on to characteristic root. This is important. 200% you're getting a question from characteristic root and generating function. 200% you will get a question. Okay. So characteristic root, what happens? I very well told you the general form and equation and homogeneous and non-homogeneous cases. What is homogeneous? Homogeneous means the right hand side is 0. Non-homogeneous, the right hand side is non-zero. Okay. I hope you are taught for both homogeneous and non-homogeneous cases. So let's first quickly go through the homogeneous case. So where you taught the non-homogeneous case, can you please confirm? No. Oh, great. Then nothing is here in the chapter. Okay. So what happens here is for an order R homogeneous equation, for an order R homogeneous equation, you will replace all these terms. There we had S, A, N, here S of K, it could be T of N or anything. It's just a function, that's it. Okay. So what happens? You will replace this S of K by R power, the order of this equation. What is the order of this equation? K minus M, that is M. Okay. So you'll replace every term by R power order of this equation. R power, this would be what? M minus 1 and so on. Getting this? So in this case, let's consider a simple equation. C naught we have a simple equation. Let's say C naught A N plus C1 N minus 1 plus C2 is equal to 0. Okay. So if you have something like that, what do? You substitute it in terms of its order. Its order, right? So what happens in this case? You substitute every guy in terms of every other guy. Let's say there's n minus 2 also here. Chuma. Okay. So you will substitute every guy in terms of its order. In this case, the order is what? R square. R square. Right. So given an equation, first find its order. One second. Find its order. So in this case, C naught R square plus C1R plus C2 is equal to 0. Okay. So every time you get an equation, very simply find R, put R square in the first term, meaning the extrememost term, then R, then constant term. Very simple. Now, when you have an equation like this is a simple quadratic equation. You can solve this for roots. You will get R1 or R2. Depending on what type they are. If they are equal and they are real and equal, then the solution is given by A R1 power K plus B R2 power K. Again, I don't know what A and B are, right? How will I find A and B? Again, our initial conditions. Without initial conditions, you cannot solve them. I mean it when I say that, right? So A R1 power K plus B R2 power K. You can just find the values of A and B there. Simple. What if, oh sorry, real and unequal case. Yeah. What if it is real and equal case? Unequal na R1, R2, two different roots, right? What if it was equal? So in equal na, R1 is equal to R2 is equal to R. In that case, your S of K would be nothing but A plus BK. A plus BK. If it was N, it will be N here. Into R power N. R power K in this case. Okay. So A plus BK into R power K. So this you will substitute and find the values of A and B. Very good. Now, what if they are complex? Their determinant is less than 0. In that case, let's assume the complex roots you get is alpha plus iota beta. You either ways have to use the quadratic formula. And R2 is equal to alpha minus iota beta. Okay. So what happens here? In this case, you will first find the value of alpha and beta, that you find it using the quadratic formula itself, right? Then you find the value of theta. What is theta? Theta is tan inverse of beta by alpha. Tan inverse of beta by alpha. Okay. And then you'll also find the value of small r. The small r. The value of small r is given by root of alpha square plus beta square. Right? This value, square it and add it up, take root. This follows from something called Pythagoras theorem. You can visualize this where in argand plane. Argand plane. Okay. So no worries. So you got theta, you got r. Very simple. Substitute in the formula. Direct formula application. Don't miss out on these very simple ones. R power k. K is just that parameter you have. R you got it root of alpha square plus beta square. A you will get it only substitute the initial condition and solve the equation. Cos into theta k. Right? Theta is the one which you have plus b into sine theta k. Yeah, that's it. Very simple, right? So let's try to solve one equation. So what happens? 1 second, please. 1 second, please. 1 second. So what happens here? You have f of n depending on f of n minus 1 and f of n minus 2. So in this case, substitute f of n. The order is what? N minus 1, n minus 2. So order is 2, right? So n minus 2 basically. So it'll be r square minus 8r plus 16 is equal to 0. I beautifully see that it is r minus 4 the whole square. So r will be what? 4 and 4. Real and equal. In that case, a plus bk into r power k. Okay. Now how will you find this is what? This is what? S of k. S of k. Okay. In this case, f of n. So let's make everything in terms of f of n. So f of n is equal to a plus bn into 4 power n. Great. Now you are given the initial conditions that those are a f of 2 is equal to 16 and f of 3 is equal to 80. F of 2 is equal to 60, meaning f of 2 is equal to a plus 2b into 4 square. This is equal to 16. 16. Okay. And f of 3 is equal to 80. So it will be a plus 3b into 4 cube is equal to 80. Just solve this equation. Simpler, simpler. So you will just eliminate this variables a and b and get either of them and then find the value of a and b. Okay. Next, when you find the values of a and b, don't forget to substitute it. Very important. Right. So f of n is equal to a plus bk. A you found as 1 by 2. N was k was n and b was supposed to be 1 by 4. Right. Into r power n. R is 4. That was we found the real and equal root, and n was the parameter. That's it. Okay. So let's try to solve this. What happens? Very simple. First, make it in the general form. The general form is putting everything on the left hand side and right hand side has to be 0. Then only it will be homogeneous. So an minus 2an minus 1 plus 2an minus 2 is equal to 0. Right? Now order is 2. So r square minus 2r plus 2 is equal to 0. Now what kind of equation is this? Real and equal or real and unequal. What are the roots? I'm not able to find the root. So let's apply the quadratic formula. So if you apply the quadratic formula, you observe that it is a complex one. Okay, great. So it is a complex one. So the root was 1 plus iota plus 1 minus iota. Okay. So in that case, what will be the value of alpha and beta? Alpha is 1 and beta is also 1. So that 1 plus 1 into iota, 1 minus 1 into iota. Right. So alpha beta, you got it. Substitute directly in the value of r. R is root of alpha square plus beta square. But this guy is testing my patience. So give me a second. So far, is it all clear? Is it clear so far? Am I complicating things? Okay, thank you. Guys, others? Is it clear so far? Yes, thank you so much. Okay, okay. Okay. Uh, just give me a second, guys. I think it should be fine now. Is it? Yes. Okay, great. So let's try to solve an example, right? So sorry guys, just give me a second. Yes, we were here, right? So we got alpha beta. Then you can easily find the value of r. That is root of 1 square plus 1 square root 2. You got r. Then we can find the value of theta. That is tan inverse beta by alpha. Tan inverse beta by alpha is tan inverse of 1 by 1. Tan inverse 1, that is pi by 4. Everything has to be in radians. All right. So this will be f of n is equal to r power n a cos theta n plus b sine theta n. Getting this? That's it. Now, after you substitute the values are a naught is equal to 1 and a1 is equal to 2 initial conditions. You put the value of n as 0 and put the value of f of n as 1. You put the value of n as 1, put the value of f of n is equal to 2. Then you will get what? You will get the values of a and b. Direct substitution. That's it. Direct substitution, right? So let's solve one more example. In this case, what happens? S of k minus 7, S of k minus 1 plus 6 S of k minus 2 is equal to 0. Will be r square minus 7r plus 6 is equal to 0. In that case, you are having real and unequal roots. So what do you do? A into r1 per k plus b into r2 per k. Just substitute that. R1 is either ways. A into 1 per k plus b into 6 per k, or A into 6 per k plus b into 1 per k. It doesn't matter. Okay. It's just the corresponding value of constant will change. That's it. Okay. So, but the overall equation will be exactly the same, right? So what happens? You substitute the value of you got this equation, but you don't know what a and b are. Substitute the initial conditions, solve the equations, get the value of a and b, and substitute it here. When you substitute, you get something like this nicely. Yeah. So yeah, so that is homogeneous case. Just quickly revising it. You have a general form of reconciliation s of k plus c1 s of k minus 1 till cm s of k minus m is equal to phi of k. Now, phi of k, if it is 0, it is homogeneous. We are only dealing with homogeneous cases. The order of this equation is k minus m, that is just m. Okay. So it will be what? If it is order 2, it will be c naught s of k plus c1 s of k minus 1 plus c2 s of k minus 2. And that you replace it by what? C naught r square plus c1 r plus c2 is equal to 0. Right? Then you do what? You do, I hope you all understand how this comes, right? So c naught r square, c1 r, and c2 r power 0. Everything, if you observe, if it is 0 here, it is, if it is c naught here, it is s of k, c1 here s of k minus 1, c2 here s of k minus 2. So in that case, you are substituting every k by r square, s of k by r square. S of k by r square meaning, if it is s of k minus 1, it would be r power 1, r power 1, something like that. Yeah. S of k minus 0, it is r, one sec. Yeah, yeah. If it is s of k, just r square. S of k minus 1, just c1 r. And s of k minus 2, it is just r bar 0. Yeah. Just see the difference of the variables and substitute accordingly. Do not complicate it too much, like me. Yeah. Real and unequal, it's just a r1 per k plus b r2 per k. Real and equal, it's just a plus bk into r per k. And complex, na, you find the value of theta and r, then put it in this equation. R per k, a cos theta k plus b sin theta k. Getting it? So I think that should do for characteristic root method. Nothing else is here. You don't have non-homogeneous case also. Now let's quickly do generating function. Just let's wait for this guy to come. Okay. Yeah. Okay. So before you go to generating function method, I want you to understand few things, few simple sequences. You should have learned it in the calculus course, but just reiterating it. 1 by 1 minus x is nothing but 1 plus x square and so on till infinity, right? 1 by 1 plus x would be the same thing with the common ratio as minus x. So it'll be 1 minus x plus x minus x cube and so on, right? What is 1 by 1 minus x the whole square? It is 1 plus 2x plus 3x square plus 4x cube and so on. What is 1 plus x the whole square? The same thing with a minus plus minus plus alternating. Okay, great. How do you define this? Very simple. You should know this general formula of a by 1 minus r, right? So yes, sum of infinite terms, right? Or in geometric progression with the common ratio of r is given by a by 1 minus r. Okay. So the first sequence we saw, the common ratio was x. So a by 1 minus x, that is 1 by 1 minus x because the first term was 1. And the second sequence we saw, common ratio was minus 1. That's why minus of minus 1 became plus 1. That's it. Okay. So quickly moving on to g of s comma z. Okay. We'll be defining everything in so if I have an equation, I want to put that equation to some form, but I don't know how to solve that equation. Yeah, let's say I don't know characteristic method or any method of iteration method. I want to solve it in another method in such a way that I'm not putting that guy, I'm putting that guy in some form which I'm comfortable with. And that some form I'm comfortable with is g of s comma z. That's it. Okay. The sum form I am comfortable with is g of s comma z. Okay. So g of s comma z is generally, it is equal to what? It is always equal to what? Summation of Sn z power n from n is equal to 0 till infinity. Please understand this. This is very, very important. Okay. Sn z power n summation from 0 to infinity. Okay. So if you expand the sequence, so whenever you have some trouble understanding these things, expand the sequences and check it. If you expand the sequence, you'll get S naught z power 0 plus S1 z plus S2 z square till Sn z power n. But it will be till infinity. But yeah, here up to just n terms. Up to just n terms. Okay. So how do you solve this by expressing that guy in terms of this guy? Let's try to understand. Let's take up a problem. So the problem here, let's say, is s of k plus 5 s of k minus 1 is equal to 9 plus 2k. You saw the homogeneous case in generating function, no? I hope you should have. You didn't see it in characteristic root, but you saw it in generating function, right? Something like this. It should be there. You should have seen it. So how do you solve this? So what you do is, first step is to make that guy in terms of our sequence called g of s comma z. How do I do that? I have something called s of k. Okay. That will define yes for me. That will define yes for me. But I don't have anything that will define z for me. Z for me. So what I'll do is, I first put everything into general form of a recurrence relation and multiply everything by z power k actually. Okay. So what happens? I'm putting my general sequence is s of k plus 5 s of k minus 1 is equal to 9 plus 2k. I've taken that to the left hand side. So it is minus 9 minus 2k is equal to 0. Beautiful. Now what I'll do? I'll try to multiply this guy by z power k so that I can bring out g of s comma k. Right? G of s comma z. So what happens here? It will be s of k z power k plus 5 s of k minus 1 z power k minus z 9 z power k and minus 2 uh, what was it? K z power k, right? So you'll get a sequence like that. You'll get a sequence like this: s of k z power k plus 5. It's the whole equation. They're multiplied by z power k. But yeah, I got something like Sn. I got something like z power n. But I've still not figured out how to find the summation. Summation Sn z power n, right? So how will I do that? Take summation fully. But where will you take summation from? Take summation in such a way the question is defined from. Okay. This guy's stopped working. Wait a second. He's giving me too much trouble. So sorry, guys. Okay, I'll shift the platform. One sec. Just give me a second. Yes. So, yes, we were here. We took summation from what to what. So they have defined the variable from what? From 1 k is equal to 1 till infinity. K is greater than or equal to 1. Take the summation from that. And that explains it. Why that explains it is because if you take it from 0, s of k minus 1 will not be defined. You cannot say what it is. Okay. So that's why define it. It should be defined in the question. If it is not, make sure that this simple intricacies like s of k or s of k minus 1, that should be defined at least, right? So k is equal to 1 till infinity. So how will I do that? Now, see every part of equation and multiply it with z bar k, right? So k is equal to 1 to infinity. As I have just split the summation to every term according to the rule of summation. So s of k into z bar k. Do you clearly see this? What is it giving you? Just expand it and check. If you expand it and check, it will give you s1 z bar 1 plus S2 Z square plus S3 Z cube and so on. Wow, beautiful. But what do I want? I want g of s comma z, and that should be what? That should be s naught plus s1 z power 1 plus s2 z square and so on. I'm not having that. So what I'll do instead is I just add and subtract s naught. Simple, right? So this whole term is nothing but my entire g of s comma z only, right? Without s naught. That's it. So this should be clear, I believe. Moving forward, what is this term telling us? This term is telling 5 into s of k summation of 1 to infinity s of k minus 1 z bar k. Okay, great. So how will you do this? Just substitute and check. So if you substitute and check, it will give you s naught z power 1 plus s1. If you put k is equal to 2, you'll get s1 z square and s2 z cube and so on. You see the pattern, right? It is, I want s naught plus s1z plus s2z square. But this guy is giving me a z higher, meaning at every term, z is getting multiplied. I don't want that product. So what I'll do is, I'll just take z common, right? If you take z common, it will give you s naught plus s1z plus s2z square, so on till infinity. Yes. So this is going to be what? S naught plus s1z plus s2z square. Simple, general sequence. So it will be what? G into z into g of s comma z. Okay. Obviously, 5 will be there, right? Done. So I got 5 z g of s comma z. Okay, very nice. Next, what will you do with this guy? Just substitute and check. Okay. What do you get? You put z is equal k is equal to 1, you get z. You put k is equal to 2, you get z square. You put k is equal to 3, z cube. Okay, interesting. Okay. Z plus z square till plus z cube and so on till infinity. Again, this is something a nice sequence I know. What is that? Arithmetic progression, right? So 1 plus, sorry, geometric progression, right? In infinite case, 1 plus z square, z cube and so on, right? So this is just the exact thing without what? 1. Without 1, right? So what I'll do, I just add and subtract 1 to it. I just add and subtract 1 to it. Okay. Or I can do one more thing. I can just take z common, right? I can just take z common. In that case also it will work. So what will be that? It will be 1 plus z square, z cube and so on. Take z common, right? I'm just displacing it by 1 z position in the product. Yeah, that should also work. Okay. So what happens here? You got something like g of s comma z in the first place, right? And you had what? You had the first term, right? A naught was not there. That is S naught was not there. You just subtracted S naught there because it was not there. Okay. Then you had phi Z G of S comma Z. And then you also had, oh, you had one more term. Okay, fine. So it was minus, so we found it as minus 9Z by 1 minus Z. So we took Z common. That was arithmetic, that was geometric progression. That was 1 by 1 minus Z. So we nicely have written this. Next, what was the other term? The other term was 2 into summation K Z power K. Now again, substitute it and check. What do you have? 1 into Z power 1 plus 2 into Z power 2 plus 3 into Z cube and so on. What is this giving me? Z plus 2Z square plus 3Z cube and so on. Again, I can take Z common, right? What it will give you? 1 plus 2Z plus 3Z square and goes on. So this will be what? Z into, this is a nice AGP. What was it? 1 by 1 minus Z the whole square. 1 by 1 minus Z the whole square. So it became what? 2 was the quotient, Z was there, 1 by 1 minus Z the whole square came. Easily. Beautiful. So you found out a way to write what? Equations in terms of G of S comma Z or some general form of geometric progression. So now the next step is finding G of S comma Z itself. Okay. We have now just expressed everything in terms of G of S comma Z. Now we evaluate for G of S comma Z. By the time evaluate, I mean to say put everything to right hand side. Left hand side it should be G of S comma Z. Okay. So what will happen in that case? Right. So G of S comma Z, you take it common, it will be 1 plus phi K, phi Z. 1 plus phi Z was the coefficient. And we very well know what is S of 0. That was given in the initial condition. Right. So initial condition, let's say it is given as 6. Okay. Okay. Great. Next, what do you have? You have this term. You had minus 9Z by 1 minus Z, minus 2Z by 1 minus Z square. Everything to right hand side. That will give you what? Plus Z into 9. I just put everything in terms of 1 minus Z square so that I can take LCM easily. So I am just multiplying 1 minus Z here, 1 minus Z here. Fine. 9Z in 1 minus Z minus 2Z, but it comes plus 2Z by 1 minus Z the whole square. Beautiful. Super. And take the 6 also that way with proper LCM. You got a nice equation in terms with the left hand side as G of S comma Z and the right hand side as what? In terms of just Z. Just Z minus. So most people put it as G of Z only. They don't put G of S comma Z. That is also fine. You will find the S at last. Okay. So you got as nice as in terms of Z. This is G of S comma Z. But still, this is not in a form that I want it to be. I cannot compare this form with any other general form I know. So what I will do partial fraction. Partial fraction is my best friend in generating function, right? So you do what? Partial fraction. How do you do partial fraction? Simple. You should know the general forms and all. If you have square and all, then what do? You do by 1 minus z, a by 1 minus z, b by 1 minus z whole square, plus c by, this is 1 plus 5z. So you separate them, split the terms, right? So this whole function is nothing but a by 1 minus, or you can replace terms as well. Just the constant value will change. That's it. Okay. So in this case, I take 1 plus 5z. You could take 1 minus z also, doesn't matter. So a plus 1 plus 5z plus b by 1 minus z plus c by 1 minus z, the whole square. Now you can write this in terms of taking LCM, right? If you take the LCM minus, so you take LCM with respect to this term. 1 minus z the whole square, 1 plus 5z. There is 1 plus 5z here, so we will multiply it by 1 minus z whole square. There is 1 minus z here, so we will multiply it by 1 minus z and 1 plus 5z. There is 1 minus z the whole square, so we just multiply it by 1 plus 5z. Okay, beautiful. So we got a nice equation like this. I have to find the values of A, B, C. How will I do that? Again, you know that this works for a lot of values, right? So you just substitute a value and check it. Okay. You substitute whose value? You put z is equal to 1. If you put z is equal to 1, this term will vanish. This term will also vanish because 1 minus 1. Right? But this term will remain. Now you can put z is equal to 1 here also. So minus 3 minus z plus 6. Here it will be c into 1 plus 5, 6. So 6z is equal to minus 3 minus z, I put it as 1. Okay. So minus 4 plus 1 minus 3. Right. So I can easily find the value of C. That is just 6 by minus 3. Minus 3 by 6. Right. It's just minus 3 by minus 6 it seems. Yeah. Okay. -3, -1, and 6 into 1 plus 5. So you easily get this -4 plus 6. I just missed that. Sorry. So what happens here? You just get 2 is equal to 6c. So c is equal to 1 by 3. Beautiful. Beautiful. Okay. Similarly, you plug it in values. What all values can you plug it in? Plug it in such a way that many terms will vanish. All right. If you plug z is equal to -1 by 5, this term will vanish, this term will vanish. Only this will remain. Right. Let's say after that you cannot vanish anything and you might have a variable to be found. You substitute any value. It has to work for that. Right, in the domain. So you can put z is equal to something like -1, something like 0, something like that. Okay. Get the value, okay, of a, b, c. When you know the value of a, b, c, you can easily write it in terms of this function. You can easily write it in terms of this function. Okay. When you know to write it in terms of this function, you can easily decompose it to the general form of geometric progression. General form of geometric progression. Okay. So sorry for the incomplete answer. Yeah. Okay. Fine. So what happens here? I found it as a by 1 minus z. A by 1 minus z. Okay. So the value of a was found to be, let's say, if I had solved the equations correctly, the value of a should be 8 by 9. Okay. So 8 by 9 into 1 by 1 minus z. What is 1 by 1 minus z? Summation of what? Z power n from n is equal to 0 to infinity. Agreed? N is equal to 0 to infinity. Z power n. If you take summation, it will give you what? A by 8 by 9 by 1 minus z. Beautiful. Similarly, b by 1 minus z the whole square. B by 1 minus z the whole square. You know the value of b. Let's say b, let's assume b is b. Okay. 1 by 1 minus z the whole square would be what? It would be an ACP, right? And that would be given by what? K plus 1 into z power k, where k starts from 0 to infinity. Why so? Substitute and check. It will give you the right answer. Substitute it, you will get 1 into z power 0 plus. If you put 1, k is equal to 1, then it will give you 2 into z power 2 and so on. Sorry, if you put k is equal to 1, it will give you 2 into z power 1 and then 3 into z square and so on. It will easily give you 1 plus 2z plus 3z square plus 4 and so on, right? You know this. Next step, what else do you have? You have c by 1 plus 5z. C by 1 plus 5z. What can you do with this? You have to, again, put it in terms of 5z. That's it. You just assume this guy as the same guy, but 5z is equal to some random x for which the GP is defined for. It will be just summation of 5z with a -1. With a -1. Yeah. Power k, where k is defined from 0 to infinity. Okay. Super. Now, after doing all that, what will you do? You will just take all the quotients of z power k or z power n, whatever. Okay. You'll take all the, so this, you will put everything in the summation form. I'll show you how it looks like. It looked like something like this. It'll look like this. You put everything in terms of this. I've written everything for you. Okay. It look like this for this problem like this. Okay. So you take the quotients of z power n. Take the quotients of z power n. In this case, the quotient of z power n would be 2 power n. 2 into 2 power n. And the quotient of z power n in this case would be just 3 power n. There is no quotient. So plus 3 power n. This will give you the answer for an. Right? This will give you the answer for an. That's it. Oh, there was a minus there. Okay. So why does it work? It works because that's the way g of s comma z is defined. G of s comma z is what? Sn z power n, right? Summation of Sn z power n. In a summation term, the Zn quotient itself is Sn only. The sequence only. The sequence quotients only. Right? If you want to find the sequence, just express it in terms of summation Sn z power n, then take the quotient of z power n. It will easily give you the sequence. That is the Sn value. Okay. So you got nicely, it is 2 power n plus 1 minus 3 power n. Did you get this? We'll do one more example and close. Did you get this? Oh, it is not visible. Oh, why? It has not been visible. Nerma. This, you're not able to see this? Okay. Thank you so much. You saved me. Okay. Now, yeah. So again, this problem, right? So what happens? This un plus 2, 5 un plus 1 plus 6 n is equal to 0 with n greater than or equal to 0 with u naught is equal to 1. Beautiful. Okay. So what do you do? First, put it in the general form. The general form is what? General form is s of g of s comma z. And that is s naught plus s1z plus s2z square till infinity. Okay. So how do you do that? In this case, first you multiply. The first step is making it in the general form. You put everything, you take everything to the left hand side. Okay, nice. Next, multiply it by z power n. I multiplied everything by z power n beautifully. And I have taken the summation from n is equal to 0 to infinity because that is how it is defined. Beautiful. Nice. Now, I evaluate each term. I put 0 here. I get u2 z power 0. And then I get u1 z power sorry, u3 z power 1 and so on. u2 z power 0 is 1, so u2 plus u3z plus u4 z square and so on. Am I fine with this? Am I fine with this? I should be, but it is still not not the general form I expect. So let's keep that on hold. Let's come back. Okay. So what do you have this? Sorry. So if you substitute it here, it will be u1 z power 0, u2 z power 1 and so on, right? So let's keep that also here. It'll be u1 plus u2z plus u3z square and so on. Okay. Next, what is this? 6 summation from 0 to infinity u1 z power n. Beautiful, no? You see this, you'll be happy. Yeah. See, it is exactly in the form I expect. It's exactly in the form I expect. u1 z power n. If you put 0 there, it will easily give you u naught. If you put 1 there, it will give you u1z. If you put 2 there, it will give you u2z square and so on. Right? So it is exactly g of s comma z. So plus 6 g of s comma z. Beautiful. Beautiful. Is this g of s comma z? Is this g of s comma z? It is not. What is g of s comma z? It is actually u naught plus u1z plus u2z square and so on. U naught is missing first point. There is no z, so second point. So I have to somehow bring both the things into place so that I can make it general form. So what I will do is I multiply it by z first. So let's say we are multiplying by z and dividing it by z. So 5 by z will be there. Okay. I'm multiplying by z. So it will be what? u1z plus u2z square plus u3z cube and so on. Wow, beautiful. Now this has been in a nice form, but you just u naught is missing. So what I'll do? Minus 5 by z minus u naught. Yeah, get this? Second, we solve this. u2 plus u3 is 4z square and so on. Again, it's not the general form I want. My general form is what? u naught plus u1z plus u2z square that and so on. So what I'll do is, firstly, what is pending? Firstly, I don't have u naught. I neither have u1. So I have to somehow bring those guys inside. Next, I have u2 z square, but I don't have z square. I have u3 z cube. There is no z cube here. It's just z. So if I just multiply and divide by z, so I just multiply z square divided by z square. Okay. Beautiful. Next, find that u naught and u and z are missing. I'll add u naught and I'll add and subtract u naught and u and z. So this will be nothing but what? 1 by z square into g of s comma z minus u naught minus u1 z. That's it. Okay. So this is how it looks like. Okay. So you will have, yeah, so this is the form, right? So you substitute the value of u naught and u1, you get 1 by z square g of s comma z minus u naught minus u1 z minus 5 by z g of s comma z. You observe that there was one missing, there was a naught missing, right? A naught was 1.
right? And then plus 6, this is perfect. Perfect term. Beautiful. Now you do what? G of s comma z all to the one side and the other terms to the other, the z terms to the other side, right? Take everything to that side, take LCM, get something like this beautifully. Okay. Now, again, this is not in a form that I would like. So I do partial fraction. But before doing partial fraction, I have to factorize the denominator, right? If it is not factorized. So I'll factorize this thing. I hope you guys know factorization. Yeah. So when I factorized it, I found that it was 3z minus 1 and 2z minus 1, right? So I can express that as what? A by 3z minus 1 plus b by 2z minus 1. Usual question is find the value of a and b. Okay. You got the value of a and b. So g of s comma z became 1, a was 1, so 1 by 3z minus 1, b was minus 2, so minus 2 by 2z minus 1. Beautiful. But yeah, I still don't have anything that helps me, right? I want everything in terms of 1 minus something, right? I don't have it in terms of 1 minus something. So what I do is I can take minus 1 common and I can do that. That also works, right? If you take minus 1 common, what happens? Minus 1 by 1 minus 3z. Okay. And then here it will be minus 2 by, sorry, plus 2 by 1 minus 2z. Minus 1 by 1 minus 3z plus 2 by 1 minus 2z. Now, I can just write it in terms of sequence, right? It will be minus summation 3z whole power n, right? Where n ranges to infinity, right? And then what will be there? Here it will be 2 summation 2z whole power n. I'm writing it directly so that you understand. You very well know the sequence, right? We very well know that 1 by summation of x power n from n is equal to 0 to infinity. The same way I'm doing it. Okay. So this is nothing but my g of s comma z. Then what is my sequence then? Sequence just coefficient of z power n. The coefficient of z power n is what? Minus 3 power n. So minus 3 power n. Coefficient of z power n here is plus 2 into 2 power n. Do you see it is the exact same sequence we got? That's it. Okay. Did you understand generating function fully? If you understood generating function fully, just drop a text. Guys, guys, I don't see any text. Is it clear or not? Okay, all right. So you got what? You got, so let's summarize everything. Let's summarize unit 4. I think that's the end of unit 4. Is there something else in unit 4? Is there something else in unit 4? Is my voice breaking? Am I audible? Okay, okay, okay. Thank you. Okay, yeah. So I just want to say that the summary is first understanding what a recurrence relation is. Then what do you mean by solving a recurrence relation? How do you solve it by iteration method, characteristic root method, and generating function method? In iteration, you keep doing looping on until you reach the final value. In characteristic root, you first express it in terms of r per k, right? So then you try to solve the quadratic equation or cubic equation if you have. Okay, we had cubic. And then you find the roots based on the nature of the roots. You define the recurrence relation. Yeah, I mean explicit form, right? And then you apply the initial conditions and find the value of constants. Beautiful. Next, that was homogeneous case, right? And then in which the right hand side was 0. Next, you do generating function in which you have g of s comma z. You define it in terms of what? Firstly, you multiply, you take everything to general form left hand side, multiply everything. Yeah, you multiply everything by z power k, and then you put it in terms of general form. It should be s naught plus s1z plus s2z square and so on. Yeah, and that's it. After that, you do partial fractions to get it to a general sequence form, and then take the quotient z power n to find the sequence. Is it all clear, guys? Am I clear? Am I clear? Is the recurrence relations clear? Guys, guys. ஏய் பேசுங்கடா ரெக்கார்டிங் ஆஃப் பண்ணிட்டேனா Is everything clear? Don't make me point out names. Okay. All right then. Can someone open your mic and speak? Tejaswini or Varshita, Kushal. Hello. Hello. Hello.
Hello.
Yeah. Hello. கேக்குதா? Yeah. Is it?
கேக்குது.
நீ எப்ப நடுவுல வந்த? இப்போ இவ்வளவு நேரம் இருந்தியா?
ஊடல ஒரு 10 நிமிஷம் வெளில போயிட்டேன்.
ஏய், எனக்கு கம்பெனிக்கு ஆள் இல்லப்பா. I was hesitant if I was audible at least. Okay, everything was clear, la.
ஓகே.
Yeah, so that was
மொத்தம்
the end
எத்தனை
of.
பேர்
So,
தான்
என்னடா
மொத்தம் எத்தனை பேர் இருக்கோம்?
மொத்தம்?
இல்ல ஓகே ஓகே கண்டிப்பா பண்ணுங்க.
Yeah, so we are done with unit 1, 3, 4. Okay. Next we have unit
Okay.
5 and unit 2. Okay. So not much thing is there for unit 5. We'll continue unit 5 by 5:15. Does it work?
ஓகே ஓகே.
And then unit 2 we'll see after that. Okay. Bye bye guys. We'll
Ah.
meet at 5:15.
Bye.
Hello, am I audible? Kushal? Hello, hello, hello.